In this video, we're going to look at linear second-order differential equations with constant coefficients. I'll explain the piece about fx equals 0 in a moment. There is the general linear second-order differential equation with constant coefficients. A, b, and c are constant, and it's second order. The right-hand side can be any function of x. In this video, we're just going to consider the case where fx is 0. Well, let's take an example. Here I have a second-order differential equation with constant coefficients, and the right-hand side is 0. First thing I'm going to look at is something which comes from the differential equation. Instead of d2y by dx squared, I'm going to write m squared. Instead of dy by dx, I'm going to write m, and instead of 8y, I'm just going to write 8. So from the differential equation, I get what's called the auxiliary equation. This will always be a quadratic for second-order differential equations. We will always be able to solve it, factorize, and this has roots 4 and -2. So in this case, our auxiliary equation has distinct real roots. Well, now we're going to do something which is a little bit strange. We're going to use the factorizing of our auxiliary equation to sort of factorize the differential equation. Have you ever factorized a differential equation before? Look at this. D by dx minus 4 sort of multiplied by dy by dx plus 2y equals 0. Let's have a look at that and just see that it does do what we want. D by dx means differentiate. So differentiating, I get d2y by dx squared. I want it. D by dx, 2y gives me 2 dy by dx. Minus 4 dy by dx is minus 2 dy by dx. Good. And minus 4 times 2y is minus 8y. So we have managed to sort of factorize our differential equation. Now I want to put z equal to dy by dx plus 2y. I'm going to call that equation 1 because I'll refer to it later. The equation just above now becomes d by dx minus 4. Z is 0, which is just dz by dx minus 4z equals 0. I'm going to use an integrating factor. We could do it differently, but I think the integrating factor is just as easy. This is e to the integral minus 4 dx, which is e to the minus 4x. Putting that in and missing out a line, we get d by dx of e to the minus 4xz. Just imagine doing that. You get there. That is equal to 0, which gives me e to the minus 4xz is a constant, which I'm going to call a dashed, and therefore z is a dashed e to the 4x. Well, let's substitute that now in 1. So going back up to look at 1, dy by dx plus 2y is equal to z, which is a dashed e to the 4x. So I get dy by dx plus 2y is equal to a dashed e to the 4x. There it is. Now let's give myself a little bit more space. Integrating factor again. E to the integral 2 dx is e to the 2x. Multiplying both sides by e to the 2x plus 2e to the 2xy equals a dashed e to the 6x. Whole purpose of doing this, d by dx of e to the 2xy is a dashed e to the 6x. Integrating, that gives us that e to the 2xy is a dashed over 6. Well, a dashed over 6 is just an arbitrary constant. Let's call it a, e to the 6x plus b. And so my general solution which is often abbreviated as D.E.s, is y equals, dividing by e to the 2x, a e to the 4x plus b e to the minus 2x. Notice that the 4 and minus 2 in the general solution are the roots, I'll show you in a moment, of the auxiliary equation. So 4 and minus 2, and my auxiliary equation, if you look at the top here, has roots 4 and minus 2. So here is an example, and every single one with distinct real roots would behave the same way. This technique does fall down if we have coincident real roots. So here is an example where we've got coincident real roots. I have again formed the auxiliary equation, m squared minus 6m plus 9 is naught. This, if we factorize, is m minus 3 all squared, which has coincident roots 3 and 3. So let's carry on and see how it works. Let's sort of factorize again. So let's suggest that we might look at d by dx minus 3 times dy by dx minus 3y equals 0. Let's make sure that that is doing what we want it to. d2y by dx squared, yes. Minus 3 dy by dx. Minus 3 dy by dx is minus 6 dy by dx, yes. Plus 9y, yep. So I'm happy with that. In the same way, we're going to put z equal to dy by dx minus 3y, which again I will call 1 because I'm going to refer to it later. The line above now gives us d by dx minus 3z is 0, which is the same as saying dz by dx minus 3z equals 0. My integrating factor is e to the minus integral minus 3 dx, which is e to the minus 3x, which will give me that d by dx of e to the minus 3xz is 0. Integrating gives me e to the minus 3xz is just a constant, which gives me z equals a e to the 3x. So if we've got z equals a e to the 3x, we now have dy by dx minus 3y is a e to the 3x. So let's substitute in 1. That gives me dy by dx minus 3y equals a e to the 3x. Integrating factor, e to the integral minus 3 dx, which is e to the minus 3x. So multiplying both sides by e to the minus 3x minus 3e to the minus 3x. And this is where the technique differs from the previous example. I now just have a constant. I don't have an exponential power of x or e to the kx or anything here. This is where this differs to the case 1. I've left out a y. Okay, there it is. Now we have d by dx of e to the minus 3xy is equal to a, and therefore e to the minus 3xy is equal to ax plus b, another arbitrary constant. And so y is equal to ax plus b times e to the 3x. And that is the general solution or D.E.s when we have coincident roots 3 and 3. So with coincident roots, the general solution is ax plus b times e to the 3x. Well, we've looked at what happens if we have distinct real roots of the auxiliary equation, coincident real roots. The only other thing that can happen is we might have complex roots. So here I have an example where we have complex roots. Look at the auxiliary equation. Solving it quickly, we get m is 2 plus 3i or 2 minus 3i. We could follow exactly the same procedure through with complex numbers as in the first example, but all I'm going to do is just quote the result. There is a general justification of what's going on in the notes. So the roots of my auxiliary equation are 2 plus 3i and 2 minus 3i. That tells me that my general solution, sorry, it didn't want to write. Therefore, my general solution is y equals a e to the 2 plus 3i x plus b e to the 2 minus 3i x. Well, they've both got a factor of e to the 2x, and I'm left with a e to the 3ix plus b e to the minus 3ix. And if you remember Euler's relation with your complex numbers, this is e to the 2x times a cos 3x plus a I sine 3x plus b cos minus 3x is cos 3x plus b I sine minus 3x is minus bi sine 3x. Well, this is just e to the 2x something times cos 3x. Let's call it c. And something times sine 3x. Let's call it d. And it is possible to choose a and b as complex numbers so that c and d are real arbitrary constants. And so this now is the general solution if you have complex roots. This now summarizes what we've just been doing. If you have a linear second-order differential equation with constant coefficients, with the right-hand side equal to 0, a, b, and c are constant, the auxiliary equation is am squared plus bm plus c is 0. 3 cases to look at. If the roots of the auxiliary equation are alpha and beta, real and distinct, then the general solution is y equals a e to the alpha x plus b e to the beta x. If the roots of the auxiliary equation are real coincident roots, alpha and alpha, the general solution is y equals ax plus b e to the alpha x. And if the roots of the auxiliary equation are complex, they must occur in complex conjugate pairs. A, b, and c are real numbers. Then the general solution will be y equals e to the alpha x, that's the bit without the I, the real part, a cos beta x plus b sine beta x. Okay, this has been quite a lot to absorb in one video, and it's gone on for quite long enough. In the next video, I will do 1 or 2 examples showing you how you use this theory. In the notes, you will find this repeated, and in further notes, you will find a justification in the general case.